Okay, so let's skip part of the subsections. The derivation is a bit complicated for those bounds, but when needed, we will check the table and we'll be able to find out. But just for simplicity, we skip some of it. We skip some of it and go to the properties. We'd like to emphasize more on the properties of the random variable. Okay, so we go up to page 63. Some of you like to refer to textbook to closely follow our lecture. So we go to point 5, limit theorems for sums of random variables. Okay, so if xi represents a sequence of IID random variables, then it is intuitively clear that the running average of this sequence, meaning that you do the summation xi and you make the sum and continue this process up to n and then divide it by n. I guess most of us have experiences of doing this, right? It actually occurs in many occasions. For example, if I ask you to measure the temperature, let's say the temperature of right now, then what you do is you take samples. You take the first sample, second sample, and third, fourth. You take 100 samples and you take the average. Right? That's what you do. The process is something like this. Or uh, let's say uh, you wanna take the distance. Let's say you want to measure the distance. Let's say for a classroom, and you measure it once, the second time, the third, the fourth, and then you take the average. So the process is like this. This average of random variables is very often. We see this pretty much in many occasions. Okay, so we are interested in the statistical properties of the average. So in some sense converge to the average of the random variables. So to to say it one more time, if you take the average of sum of random variables, uh, in some sense it will converge to the average of the random variables. But the point is, uh, this is not a very accurate statement. Uh, how come? How come? Let's say you have ready. Let's say you have ready. So ready is something like that, right? Something like that. This is ready. If you take the average, this is not symmetric. If it's not symmetric, then you sum it up, you take the average. Would you expect that it goes to the average of the random variable? Of course not, because there's not symmetric. So it will say in some sense, right? It's not mathematically accurate. But it's just uh, in a sense that we think we we will approximate that this average converges in some sense, but not accurate. Okay, so um, so this is what we should understand, and the more numbers, the larger the numbers, the closer it is. Okay, so two limit theorems, that is the law of large numbers and the central limit theorem, state how rounding average of random variables behaves as n becomes large. So the law of large numbers says that if X is a sequence of IID random variables, then 1 over n summation, which is the average of the random variable, converges to the expectations of the X. Okay. So it's convergence almost everywhere and convergence almost surely. So regardless of the statement, we should think that if you take the average of large number of random variables, then it converges to the expectation. So that's the property. And then the central limit theorem states that if X is a sequence of ID random variables with M equal to expect of Xi, sigma square equal to variance of Xi, then we have summation of Xi and taking average minus M. M is what? M is the mean. M is the mean. So if you take the average of the mean, you take the average of the random variable minus the mean, and then you divide it by sigma over square root of M. It converges to standard Gaussian. That is standard normal, right? This is standard normal. Then how come? Think about this. You have divided by M. No, not divided, subtracted. You subtracted by M. And you divide it by sigma over square root M. This is the normalization, right? This and this process is called normalization. Normalization. This is called normalization. So you normalize it, then it will be normalized to standard normal. Okay, so yeah. Okay, so that is the convergence. And then let's talk about complex random variables. So a complex random variable z equal to x plus jy can be considered as a pair of real random variables x and y, and therefore we treat a complex random variable as a two-dimensional random vector with components x and y. The PDF of a complex random variable is defined to be the joint PDF of its real and complex part, right? So think about this: you have complex random variable. It looks difficult at the first sight, but what we do is we consider it as a pair, meaning two. You have two real random variables. So we treat it like two random variables with real part as one random variable and the imaginary part as the second random variable. Then we deal with it just like when we deal with the multivariate random variable, multivariate real random variable. Okay, so that's the way we think about it. And if x and y are jointly Gaussian, and z is a complex Gaussian, the PDF of a zero mean complex Gaussian random variable with IID real and imaginary parts is given by. I'm sorry. It's given by this Okay, so what's this? It's P of z equal to 1 over 2 pi sigma square exponent minus x squared plus y squared divided by 2 sigma squared. So it's in fact 1 divided by 2 sigma squared exponent minus z squared over 2 sigma squared. That is for complex random variable. And the mean and variance are defined by respect of z. Then of course you have two real, right? You think about it as two real Gaussian. So if you take the respect of z is equal to respect of x plus j respect of y. J can think this is a imaginary index, but we think about it just like treat it like a coefficient. So and it's simple. Variance of z is respect of z squared minus respect of z squared, which is the variance of x plus variance y. Two real, right? Two independent real. And then complex random vectors. Complex random vectors. A complex random vector is defined as this, and again, this is a column vector, column vector, column vector. Okay, so for x and y are real value random vectors of size m. We define the following real value matrix for complex random vector z. And C of x is respect of x minus respect of x, x minus respect of x transpose, right? This is what? This is a covariance matrix for a column real random variable, right? A column random variable, meaning it's the covariance matrix of a vector of random variables. And this is the same, it's a vector random variable. And then cxy respect of x minus x, y minus respect of y transpose. Cyx is y in front and x at the back. So matrices x, cy are covariance matrices for random vectors. And they are symmetric and non-negative, definite. It is clear from above that cxy is equal to c transpose xy. As you can see, if you take the transpose for this, it's going to be like this. Then the PDF of z is a joint PDF of its real and imaginary part. So if we define a 2n-dimensional real vector, zeta, z total equal to x and y, then the PDF of complex vector z is a PDF of a real vector z total. Okay, so it's a repermutation. We permutate that vectors differently to permutate real and imaginary part. It is clear that CZ, a covariance matrix, can be written as CZ delta equal to CX, CY, CXY, CYX, so on and so forth. So you put it into a matrix. So as I say, if we look at the dimensions, this is 2n by 1. This is 2n by 2n. Right? Make the dimensions clear and then easier to understand. So we also define the following two in general complex value matrix. CZ equal to respect of z minus ez, z minus ez, Hermitian. Okay. CZ total equal to e respect of z minus ez multiplied by z e z transpose. So this denotes the transpose, and this denotes the Hermitian transpose. So CZ and C delta are called covariance and pseudo covariance of a complex random vector Z. It's easy to verify that for any Z. For any Z, the covariance matrix is Hermitian and non-negative definite. The pseudo covariance is skewed Hermitian. For these definitions, it's easy to verify the following relations. So we can have these relations. Okay, so CZ equal to CXC plus CYJ, CZ delta equal to this. CX is CZ plus CZ delta and take the real power 1/2. CY is CZ minus CZ, take the half. And again, imaginary power and imaginary power. Okay, so we have properties. In relationship between CZ delta, and CX, CY. So we have all kinds of properties. Okay. I think we will stop here, and then that'll be end for today. And thank you.